Participant, please mute yourself, Amma.
Okay, fine. So, but in real world, the attributes are actually dependent on each other. But why? Because you see, if I take the example of length and width of a component in the earlier example in linear regression, so there is a dependency between length value and the width value, right? It is, we have estimated the what is say length information of a length of an component or an equipment given the width information, right? That means there is a dependency, but this dependency is assumed to be independent in naive Bayes classification process, which is actually violated in real time, right? In real time there will be dependency among the given set of attributes, right? So with this assumption, your Bayes classifier will now become to a naive Bayes classifier, and this assumption is crucial in technically because if you don't assume like this, in the independence conditional independence among the attributes, what happens is the computational intensity of the of this algorithm increases exponentially, right? The computational cost increases exponentially if this assumption is not made. Because of this assumption itself, the entire the computational cost is reduced to multiplying individual attribute probabilities or individual feature probabilities, right? Thereby what happens, it is simply the multiplication cost rather than the exponential cost, right? So the computational cost has dropped down to greater extent because of this assumption, right? One thing is, in order to move in the forward direction, this assumption holds good. That means to simply work with the attribute, this assumption holds good. The second thing is the exponential cost, computational cost, it has been reduced to multiplication cost, right? Now, how the mathematical modeling of the naive Bayes classifier looks like, right? You see, this is the mathematical model. So please don't look into the remaining part because we haven't gone through the mechanical engineering scenario. Before that, we just see how the mathematical modeling looks like. The LHS is nothing but the model, probabilistic model, P of y given x, which is nothing but probability of hypothesis given instance data, is equal to the likelihood. So I once again request the participants to mute themselves and listen to the session. I hope you will cooperate with me in this regard. Thank you. Right. So the probability of hypothesis given instance data is nothing but the likelihood probability, which is nothing but probability of instance given class label multiplied with the probability of the class label divided by the probability of the instances, right? So here, if you observe the numerator, the first three probabilities is because of the conditional independence assumption, right? We are simply multiplying probability of x1 given y, probability of x2 given y, and probability of x3 given y. If you consider there are only three attributes in the data set, right? So these probabilities, these three probabilities are nothing but likelihoods, right? The likelihood of instance being x1 given instance belonging to x1 given the class label is some 1 or 0, right? Class label is some 1 or 0. Now, in the same lines, what is the likelihood of instance belonging to x2 given the class label is 1 or 0? Because we are talking about binary classification. So here we are simply substituting the value of y to be either 0 or 1. In the same lines, what is the probability of uh, uh, instance belonging to the attribute x3 given the y value is 1 or 0? Right? The first part of probabilities are nothing but likelihoods. The second probability, that is p of y, is nothing but prior. In naive Bayes terminology, that probability of the class label is nothing but the prior information. So the probability of what you say 0 from the given data set, which is nothing but the number of training instances belonging to that particular class label, right? So in this particular example, there are 150 records in which 75 records belong to class label 0 and 75 records belong to class label 1, right? So there is an equal proportion of the examples, training examples, under these two class labels, right? So we are multiplying likelihood with prior in the numerator, and we are dividing with the probability of the data, right? Probability of the input data. So this RHS expression will get evaluated and get reduced to a probability value, which is nothing but the probability of the class label being 1 or 0 given the instances values are so and so. So the LHS is particularly it is of useful you it is of use when you substitute a test example, unseen example, for which you don't know what is the class label value, right? You don't know the value of y, but you know the values of x1, x2, x3, right? So which here LHS is nothing but your model. RHS is nothing but the what you say, the patterns that are utilized from the data set in order to generate that LHS value, right? The model value. Any doubts here? Yes, any doubts?
No, sir.
Fine. So now we'll come back to the previous slide where we need to understand the scenario here. The scenario considered for this particular classification or classifier is quality control in gear manufacturing. So we know that if inspection, if quality is done continuously, or if it is monitored for if it is inspected for quality in the continuous manner, then the manufactured gears will be healthy, or else if you overlook during the inspection process also, this might lead to the failed gears, right? Understood. So this based on this particular concept, there are various tasks, repetitive tasks that will happen, that are present in the gear manufacturing process. So the data acquired from that particular tasks, from that particular task, are used for this classification process, right? So the mechanical engineering team wants to implement a quality control system using this classifier to detect and classify defective gears, right? So what are the attributes that are considered for the sake of classification process, and or for the sake of learning a naive model, mathematical model is like this. Now coming to this, you see on the left hand side of the slide, we are considering three attributes. The first one is dimension of the gear, the second one is the hardness of the gear, and third is surface finish of the gear, right? So, and what we are saying is, based on these three attributes, it is possible to predict the class label of an unseen gear with the corresponding x1, x2, x3 values, uh, to either assigned with either 0 or 1, right? Either good or poor, right? So now what happens is, we substitute the corresponding values, x1 value, x2 value, x3 value of the test example on LHS, And what we do is, for y is equal to 0, we will calculate the probability, and for y is equal to 1 also we will calculate the probability. We assume that initially y value is 0 and we calculate the probability, and we also assume that if what happens, what is the probability if y value is 1. So what we do is we obtain these two probabilities on for the test records or the unseen data, and what we do is we will call max function. We will call max function, and we supply these two probabilities for of these two class labels, and this max function returns that class label that probability for that class label information whose probability is high, right? Whose probability is high. So here for test record, this is what is actually happening, right? Probability of y is either 0 or 1 is only understood uh, when the values are inferred or analyzed with max function, right? So for the sake of what you say simplicity purposes, we can consider the values of x1, x2, x3 as follows. X1 could be low, medium, high. X2 could be soft, medium, hard. X3 could be rough, medium, smooth. You can actually map them to the numbers also, right? 0, 1, 2, right? Accordingly, right? You can map those values. Right now, by substituting these values and working on the naive Bayes classifier, the prediction says the gear is predicted to be defective for a given test example. And what do you mean by 0? 0 is nothing but defective gear. 1 is nothing but non-defective gear, right? So you see the unseen example, when it is getting substituted, it has been predicted as defective. So the model is predicting the label for the input gear data, right? In terms of its attributes. Any doubts here?
Sir, Santosh sir, there is one question in the chat box.
Yes, yes. The question is are all attributes discrete? So here, that's what here, for the sake of simplicity, the values are assigned as discrete values for these attributes, so that the participants will easily follow what kind of values these attributes will take, right? Actually, the values are coming from the measurements while you perform the task, right? So those values you can use it here. Those could be continuous values. No, in real time, these attributes will hold only continuous values. I hope I have answered your question. Okay, fine. Now we'll go to the last classifier under supervised learning, that is k nearest neighbors. So k nearest neighbor is interestingly, this particular classifier can be used as both supervised model as well as unsupervised model, but we are using this as a part of supervised model in this discussion, right? And the most interesting point with this classifier is, this classifier is useful as both classification is useful as classifier as well as regressor, right? It can be used for classification as well as for regression, right? Here this KNN is a lazy model. This KNN classifier is said to be a lazy model. Why? Because until and unless the what you say test example comes to it, in the sense, what you say, until and unless the calculations are finalized, only then it will come to action to say that this particular example belongs to this class label, right? And all the remaining classifiers that you have seen previous are what you say, what is the opposite of lazy, right? Eager classifiers. Those are said to be eager classifiers. So the eager classifiers, what the eager classifiers do is, whenever the test example comes to them, they immediately apply onto the model and they say that this is the class label for you, right? But a lazy classifier, what it does is, it takes the test example, it compares with the remaining other examples which are nearer to that particular region, and then comes to a conclusion, right? It takes time to provide the conclusion. KNN classifier, right? And KNN classifier is a non-parametric classifier, right? Meaning there are no estimates which are to be found out by the model, right? No need to work on the parameters here. No, it is not a parametric model, it is a non-parametric model, whereas the other classifiers that we have seen till now are parametric models, right? So in what to say, in naive Bayes classifier, we are identifying the parameters, right, in terms of probabilities, and in likelihoods are nothing but the parameters in naive Bayes classifier. And in what to say, in logistic regression also we have coefficients and parameters in the mathematical model, right? uh, like these, those are parametric models, whereas KNN, if you see the mathematical expression of a KNN model, it does not hold any parameter, right? You see, now the mathematical expression of this model for the sake of classification is this. So for the sake of regression, we have another formula which is not required at this point of time. For the sake of classification, this is the formula. So argmax of sigma I equal to 1 to k indicator function. So this indicator function either returns 1 or 0. If the condition is true, it returns 1. If the condition is false, it returns 0. So how do we frame this condition? It is nothing but it is a three-step process uh, for whenever an unseen example comes into picture, right? So whenever a new test example is passed on to this classifier, KNN classifier, what it does is it calculates the distance between the new point and all the other points in its vicinity, right? In its vicinity. So once it calculates the distance between them, it sorts the distances in the decreasing order, and it sees uh, what are the class labels specific to those examples, nearby examples. What are the class labels specific to those nearby examples will be seen by the classifier, and assigns that particular class label to the test example which is repeating multiple times, right? So this is the what you say, performance of this particular KNN. This is the algorithm of the KNN, right? This is the way the KNN works. So this KNN simply assigns the class label, as you see, simply assigns the class label, and it does not has any parameter, right? So what is the condition? The condition is how many number of examples are with the same class label. So majority voting is the condition here. If majority voting is present, it returns the value 1 or it returns the value 0, right? So what are the features? What is the scenario that we are considering here? The scenario considered here is predicting equipment failures in a manufacturing plant, right? So the equipments are subject to wear and tear over a period of time, and if you don't take into consideration this wear and tear information of the equipment, this leads to unexpected breakdowns, right, which may lead to downtime and production losses, right? So in order to overcome this problem, the mechanical engineering team wants to use this KNN model and come up with certain predictions, right? So the attributes taken are right? Features from that in the data set could are operating parameters, sensor readings, maintenance history, and some other attributes, right? So these are the attributes considered in as part of the data set, and this data set is applied to the KNN classifier, and it says with this data set it forms a KNN model, right? It forms a KNN model, and that to that KNN model, if you supply a test example, the prediction or the class label given by the model is, and it is what you say, there is no failure of the equipment. In terms of message, we have printed that equipment is likely to continue operating normally, right? So it returns 0, right? It has returned 0, which means it is normal, equipment is normal, right? And this is pretty useful if this kind of prediction is done pretty much early, and if it returns that the equipment is about likely to fail, then immediately you can check with the department, maintenance department, and finance department, and you can replace with a new equipment whenever it is the time, right? So thereby the downtime you are reducing to a greater extent, and cost of the what to say maintenance also comes down to a greater extent. Okay. So with this we complete the supervised learning topic, and the important point to notice, the success of this supervised learning relies on having high quality labeled data for training and testing, and the choice of the appropriate algorithm for the specific task at hand. Actually speaking, one should consider more than 4 or 5 supervised learning algorithms, and they should which compare the results of these classifiers on the test portion of the data, and interpret the results inside and come up with a conclusion that this particular classifier works well on this particular scenario, right? So not all classifiers are useful on a single task. Only one particular classifier stands out, and you should identify that it is only possible with comparison of the model performance, right? So thank you for the participants. So we have completed the theory aspect. Now immediately I request all the participants to stay in this session only. Immediately we will switch on to the lab sessions, right? So if possible, SPM may be covered in the due course. If time permits and everything permits, I will try to cover this SCM also, sir. There is no issue, right? So okay, we will now switch on to the lab sessions. Okay. I request all the participants to load. 1 minute, I will tell which particular file we will work first, right? Yes, we will work with the KNN classifier first, right? Please load the KNN Python notebook file. All the participants are informed to upload the KNN file. Upload. So I think all the participants are able to uh, load this file, Python notebook file. Yes, participants, please respond if you are seeing the same screen.
I think, sir, they should go once again to collab and
So since 2 days we are making them understand the same thing. If anybody are still having any doubts, please let me know in the chat box, so that once again we will repeat the same task. But this time I request all the participants to be attentive and to concentrate on the thing that we are trying to do.
means if any new participant is there, it will be a problem, sir, because they can't understand, na, sir. If any new participant,
Okay. So what I will do is I will simply run through the once again I will go back and use the steps, follow the steps to enter into the collab. So now I request the participants to what you say, concentrate here. So Google, I am going to the Google, right? In this Google, I am typing Google Colab, right? Google Colab. So now what I am doing is I am clicking on this welcome to collaboratory link, right? This is the one of the many results that we have seen. This is the important link. So I'm clicking on this, right? I am here now, right? I am in this page. I think all the participants might have reached this page, right? So once you are here, on top right side corner, you have a button called sign in. Click on this button, sign in, right? So now once you click on this button, you will be asked to enter your Gmail credentials. So please enter with your Gmail account, Gmail details. Right, and then click on next. So you will be taken to Google Colab environment with by logging into your Gmail account. Any doubts?
no, sir, you continue, sir.
Fine. So now what I do is I will upload today's labs Python notebook. So in order to do that, I am clicking on this upload option, right? So this upload is asking me to browse the required file to upload. So what I am doing is I am selecting the KNN Python notebook file and I am clicking on open. So this will upload the Python notebook file into the Colab, right? All the new participants, I hope you are following me and you are in this particular window now. Any doubts till here? Right? So if you have no doubts, I will continue from here. Now what I need to do is before understanding this problem and running through this particular code, what I should do is I should connect to the Google Colab what is to obtain the resources like this. what you should do is I should simply click on connect here. Connect. And this will provide me the RAM and disk space from the Google Cloud. Right. So these are provided by the Google, and we are using the cloud space of the Google for doing our demonstrations, Python demonstrations, right? Now, once the RAM and disk spaces are allocated, now what I am doing is I am mounting my G drive, Google Drive. Uh, which Google Drive gets mounted with what Google account you have logged into the Colab, that Google Drive will get attached here, mounted here. So in order to do that, you simply click on this files icon, right? So this files icon, in this files icon, there is an option called mount drive. Why we are attaching actually this Google Drive? Because if at all you have huge size data, and if at all if you want to upload any files on the fly immediately, if you want to work with some images or some documents when you are doing a program, you can do that easily by having the drive attached to this Google Colab environment, right? So for that, what you should do is you should simply click on this mount drive icon. So this will ask me to run this cell. So when I run this cell, what happens is it asks me to authorize, so that uh, I am giving all the allow permissions to that to access my Google Drive. Colab will now access my Google Drive completely. Right. So to see whether my Google Drive has been attached or not, so click on this particular refresh button. So you see my Google Drive has got attached here, right? Drive, my drive, right? And I could able to see the files and folders present in my drive, right? Fine. So please let me know the participants if you all are with me till now in the chat window. Okay. So I will wait for another 1 minute based on the request of the participants. Uh, uh, please be what is say? Please be attentive. I think you are attentive, but still, as we are running out of time, we should be on toes in this regard, right? Okay. Just refresh, click on the refresh button so that you will be able to see your drive. Yes. Now I assume that you people are with me, so that I can move on. See here, I am importing certain packages in order to carry out the task of prediction. Right now, what I am using NumPy package and Pandas package. By now, most of the participants have understood the significance of these two packages, right? These two are pretty much important in machine learning, right? So NumPy package and Pandas package, right? And then we are also using what you say sklearn package. So this sklearn package is specifically it is used for machine learning for tasks, right? In order to fit a model, in order to predict the class label based on the model, fitted model, and for all those things we can utilize this sklearn package. And under model selection module, we have a submodule called train text split, right? So train text split we are using here. And for pre-processing of the data, if at all any transformations is to be done or any normalization is to be done, you are using standard scalar here, right? And then you are also defining the nearest neighbor classifier, which you want to use, right? K nearest neighbors class you are using here, right? And then the module metrics you are using, this metrics contains the variables accuracy score and classification report, right? These are functions, right? Accuracy score and classification report functions. We are using those functions here, right? So sklearn package, whatever are required for the purpose of model learning and model prediction, we need to import them, right? We need to import them. So now the first thing is we are generating random examples of thousand what you say 1,000 rows with 4 features, right? 1,000 with 4 features, and we are specifying the seed value to be 0, right? The seed value to be 0. What do you mean by seed value? You can assign what you say the seed value to be a 42 or some other value also. What do you mean by that value? So if you assign seed value to be 0, it means your values, there will be no non-determinism in that generated data. There will be no randomness in the generated data. However, you are generating synthetic random data by using random method. Those values will be fixed if you use seed, right? The values will not change from time to time. As a random function, the nature of the random method is to randomize the values. But when you use seed, what happens is once the generated random once the random values are generated, they will be fixed, right? Now I think you have understood the importance of this random method, sorry, seed method, right? Seed method. Okay, now after this, what you are doing is you are framing a data frame, right, on the pandas package. So and you are saying that these are the attributes and this is the class label. Failure is the class label, and these are the 4 attributes that you are using: temperature, pressure, vibration, and operating hours. So what is the scenario that we have seen in the KNN? Equipment failure, right? Equipment failure prediction you would like to do. So what we are doing is we are using 4 attributes: temperature, pressure, vibration, and operating hours. And yes, and the temperature values are in the range 50 to 100, pressure values are in the range 20 to 60, and vibration values are in the range 0 to 10, and operating hours are in the value 0 to 10,000, right? So for all the 1,000 samples, the values are distributed in this range only, right? So, and what you are doing is you are saying the failure is a 2-class label with on the size 1,000 records, right? For every record, you either present a value 1 or 0, right? Now what you are doing is you are splitting the data into features and class label. You would like to inform uh, you would like to inform the interpreter, Python interpreter, that what are x values and what are y values, right? So you know X values are nothing but the attributes, Xis are nothing but attributes, input attributes, and Yi is nothing but the data labels, target labels, class labels, right? So you have specified this. Instead of specifying all the four names, what is the intelligent way to do this? Instead of specifying four, the four are available here. What you're doing is simply dropping failure, which means X contains the remaining four, right? So this is the way you are using X, you are specifying X and Y. And now what you are doing is you are using the method train test split method to split X and Y values into these four sets, these four values: X train, X test, Y train, Y test, right? X train comma Y train will be one pair, X test comma Y test will be the other pair, right? So X train, Y train is the training set data. X test and Y test is the test set data, right? And what you are saying, you are explicitly specifying the size of the test set should be 30% of the 1000 samples. Of the 1000 samples, you are saying the size of the test set is 30%, which means 300 examples go into test portion of the data. Remaining 700 examples go into training portion of the data, and you are specifying a random state to be 42, right? Random state to be 42. This is also fixing the what you say, random, from the random position you are counting 300 records, and those 300 records are fixed for the test process, test portion of the data. Now what is the next thing that you are doing? You're transforming X values, right, into scaled values. So why this is so? Before understanding why we need to transform, what we are doing is we are simply saving this generated data into CSV file, to underscore CSV. We have a method called to underscore CSV. So upon data frame, what you are doing is you're simply calling this method, and you are simply passing the argument of the file, which will be generated once you run this, right? So my file is KNN features data, KNN features data, some name, right? A relevant name, and I am giving the extension .csv, right? So data.csv, I can able to now have that filled in data for all these four or five attributes, right, in this CSV file. Right now, now what I do is, in order to see the file, I am just running this code initially. So I will run this so that I am able to see the file, generated file. You see the file got generated here. So I'm downloading this file, and I would like to share this file in on the screen now initially, uh, so that when you run the same file code, you are able to download the same thing, right? I would like to once again share the screen with that Excel file. See here how the data got appended. Let's see how the data got appended for 1000 records. So you can scroll down. Right, for 1000 records, the data got appended. So you see all the values are real values or continuous values. Right? Any doubts here? Any doubts? Sir, can you explain what does a random state defines? Right. So random state specifies a random ID. Here, if you see, I say 42. 42 means some 41 if I consider. Right. This is a random state. Right. So this 41 helps the interpreter to collect 300 records from 41 and keep them useful for test portion, as test portion of the data, right? Remaining all records are once again merged to form training portion of the data. Okay. and that file is fixed. Okay, any doubts? So now we have got the data. Okay, fine. We have got the data. Now what we are doing is we will and now we have seen how the data looks like. And now what we are going to do is we will you see why we need to transform. That is the most important thing. So here temperature values, pressure values are very much similar, whereas vibration and operating what is this attribute, operating hours values are different when compared with temperature and pressure attribute values. So that's why we need to transform this data, right? There are various transformation techniques available, so we are using standard scalar method to transform, right? So after transformation also, how the data looks like is can be understood, right? So I will share this screen once again, the code screen. See the code screen. Now after transformation, right? So extra we are using standard scalar method, and what we are doing is we are transform the x train and y x test data, right? So that you will have the you will have all the attribute values falling in the same interval, right? So now what I do is I would like to create a new data frame. New underscore data is equal to what is this? Our data frame is data dot data frame, or we will create a new data frame. Let us say pd dot data frame, p dot data frame of what we have, what are the attributes we have, or we are holding what x train scaled and x test scaled. We would like to see these values, right? Specifically how the data looks like. X underscore, let us say shift x, what happened, that's okay, x underscore train underscore scaled, right? X underscore train underscore scaled comma x underscore test underscore scaled. So this is what is my data frame, and I would like to once again view the data. New data of head, let us say dot, we have, if at all we have head method, we are able to see the values of head. So yes, we have the method head, so simply call this method and simply run this. So what is that is showing? Index data must be one dimensional. Okay, so we need to pass. Okay, once again. Okay, so now we will check. Fine. Head values, where the head values are. So fine, I will generate as a new into an, I would like to save this entire thing into a new file, to underscore csv. What is the method that we have? What is the file name? Let us say I will consider a new another file name. Something like modified or transformed. transformed data .csu file. Now we'll run. Check whether the file has been generated. Yes, it has generated, and now we'll see the data. So it has converted entire thing into 0 and 1. Okay. So what it has done is, 1 minute. It has converted it to binary label. It has converted it to binary label, and that is stored in this transform data. Right. Fine. So okay. So you have done the transformations, but no issue. The next thing you are doing is k nearest neighbors classifier, knn classifier. And here, if you see, what I will do is I will import this statement, right? I will import this statement, copy this cell into the new cell here down. Where is this? In the why this entire thing has come? So delete. My point is this function itself, k nearest neighbors. Copy, paste. Why all these things are coming? So I would like to show you only these things, right? Remaining things, I would like to make you understand what are the hyperparameters. So see here. So if you see carefully, I am removing this n underscore neighbors value, and I am simply placing the cursor on the method. See, this particular k neighbors classifier is having some 6 to 7 attribute parameters, 6 to 7 parameters, right? So these are nothing but the hyperparameters, right? This function parameters is nothing but hyperparameters. Today morning we have discussed in the class, right? So what are the hyperparameters that a user can tune? The number of neighbors, and the leaf size is to be 30. The metric can be converted to any distance, Euclidean distance or Minkowski distance, and the number of jobs and metric params are none, right? The thing is, if it is a regression model, if this is a regression model, then the weights values are also can be specified, right? So as I place the cursor here, if you see, it should show up, right? As you have seen, yes, weights is uniform. It is saying if at all it is a regression model, you can use the value of weights to be random or it can be uniform. As this is not regression model, you need not care about that particular hyperparameter, right? So here I will show you how to generate multiple knn classifiers by just modifying these hyperparameters, right? So before that, we will see any doubts are there. Right now, you see, n underscore neighbors is the first value. N underscore neighbors, you can specify your wish. You can specify how many number of neighbors you would like to have as the number of nearest neighbors, right? And what without without specifying all these things, I would like to run this, and I would like to what you say, what print something, right? Print knn, let us say, right? So simply run this. It is this. So you are using the same step, right? K nearest K near classifiers nearest neighbors equal to 5, n neighbors equal to 5. So what is this? It is saying init method got an unexpected keyword argument n underscore neighbors. What is the spelling of neighbors? Neighbors. Oh, GH, right? GHBORS. Fine. We'll run this. So, in order to know whether this is a class, whether this is a new model or not, what we will do is we will simply create another classifier, KNN classifier. What we do is now we are also appending what another hyperparameter metric. Metric, yes,
टोटल देखो लास्ट अमाउंट कितना हुआ था टोटल पूरा टोटल 3496
Euclidean. So Euclidean distance I would like to use to find the distance between the test example and training examples, KNN1. It is simply showing me up what kind of a classifier that I have used. So to see how that classifier is working, right? What we need to do is we simply replace here with the name of the with the particular model, right? So first we run with this, the nearest neighbors to be 5. So what is the accuracy of the model? 49.67%, right? 49.67%. Now what I am doing is I am adding now the metric information. Now what is the metric information that we can consider? Euclidean distance, right? Euclidean, right? Now I would like to run this. By including this metric, do we have any change in the accuracy, right? So we don't have any change in the accuracy. You should also see what is the what is the pressure and accuracy values for these two class labels. Now I will change the Euclidean measure to Minkowski. Minkowski distance. We'll check. So still there is no change, right? So hyperparameters are not influencing the what you say, the performance of the classifier in K nearest neighbors, right? Now, now you please tell me from the morning discussion, uh, hyperparameters are useful uh, to to obtain the desired accuracy of the model, right? Desired accuracy of the model. Right, now you are adjusting these hyperparameters and you would like to know what is the, I would like to have some 60 or 70% accuracy, but are we getting this here? No, right? Now with five nearest neighbors, the accuracy is seem to be 49.67. What if the number of neighbors are reduced to 3? And you need to check this. Now you see the difference. All the participants, are you able to see the difference now? Yes. As participants, I would like to have response from you. Yes, are the participants with me? So you would like to have a repetition. Fine. Now, did you understand that these are the hyperparameters? Yes. Yes. So fine. Now what we are doing is we are simply modifying the values of these hyperparameters. Earlier, the nearest neighbors, the number of nearest neighbors was 5, right? Was 5, and the considered metric distance metric to be what is a Minkowski. Now, if that is the case, the accuracy value is 49.67%. Now, this is one model that has been generated, right? This is one model that has been generated with number of nearest neighbors find. Minkowski is the distance metric. Now, what I am doing is I am reducing the number of nearest neighbors to be 3 and keeping the metric as same, right? Metric as same, distance metric as same, and I would like to check whether there is any change in the accuracy levels. So this leads to improving in the accuracy, model accuracy. Is that right? Right? Does this model keep learning when we change hyperparameter? Yes, it is learning and generating a new model again and again. This is a single model will not keep learning. Whenever you modify a hyperparameter, a new model will be generated. Where do we store old model? So there are techniques today with which you can save the model, right? I need to explore it today evening, and I will show you tomorrow in the lab, right? How to save the old model, and you can also recall them also, right? You can also recall them whenever it is required. That is there, right? Now see here, now I will change this to instead of using Minkowski distance, I would use Euclidean distance. Does this change has any effect on the accuracy? We will now check. No, the distance metric does not show any impact on the accuracy of the model. The only attribute that is showing impact, or the only hyperparameter that is showing impact on the model, is the number of nearest neighbors. I think all the participants have observed this point, right? Any doubts? Yes, participants, any doubts here? Fine. I hope you have understood this particular KNN. So what is the statement? What is the statement that we have received before checking the decision message? What we are doing is, after on the learned model, what we are doing, we are predicting the test portion of the data. We are supplying the test value. See here, we are supplying the test value, and we would like to come with a class label information saying that whether this is whether the equipment will fail or operate normally, right? Now we are passing this test example. You see, out of the 4 attributes we are passing, temperature value we are passing, pressure we are passing, vibration and operating hour values are passed here, right? So once these values are passed, and what we are doing is these values are sent for the prediction on the learned model, KNN model, right? So based on the obtained prediction value, if the value is 1, right? If the value is 1, what we are printing, failure is likely. If the else means if the value is 0, we are saying that equipment will continue operating normally. So what is the message that we got? Equipment is likely to continue operating normally. Okay, any doubts? So maybe tomorrow, can you please explain how running this program and changing hyperparameter keep model learning? Any program should generate same output if running it multiple times. So sir, you should understand the basic point from the morning session, that whenever you are modifying the hyperparameters, you will generate a new model. Please try to understand. The performance of the model depends on the set of values that you pass for the hyperparameters, right? So accordingly, the model, a new model will be generated, and it is the task of the machine learning engineer to select the best model out of the list of models. In computer science terminology, we say that these list of models to form a hypothesis space, right? So from this set of models in the hypothesis space, we need to identify a good hypothesis that is consistent with the training examples, right? That is what we are trying to do here, right? Is there any setting to inform model to learn from new data hyperparameter? Uh, model is learned, model is improved. Actually speaking, this question was actually addressed in the today's morning discussion itself. What I have done, what I have given is, if you are adding up new data to the existing data, there will be a single model that gets updated from time to time, because new set of patterns are incoming. That particular model will now accommodate those new set of patterns, right? In that case, when you add new data, there will be a single model that gets updated. But when you modify the hyperparameters, model hyperparameters, class, or what you say, machine learning algorithm, supervised learning algorithm hyperparameters, then automatically you will be obtained with a new model. Okay. Fine. Right. This is one example. If you want to see the plotting of this in terms of its decision boundary, right? We worked with the three nearest neighbors. So for the three nearest neighbors, the plotting looks like this, right? Across feature 1 and feature 2. For feature 1, feature 2, we are doing bivariate analysis. So we see the scatter plot, right? So we see the scatter plot here, right? Now you see, so 0, the color blue represents 0 and color red represents 1. So there is a decision boundary separating the set of all 0 examples with 1 examples, right? So this is the KNN decision boundary as you see here, right? And this decision boundary is clearly separating, let us say, positive examples with the negative examples. Okay, any doubts here? So what I do is, I will go to the next, I will upload the next file. File, upload, browse. So the next thing that we are going to see is Navy-based quality control in gear manufacturing. The second program that we are considering is Navy-based Python notebook file. So all of you are informed to simply upload this Navy-based quality control file. So you see, are the participants with me? Please respond in the chat box. So with this, we will end this lab, right? So please pay attention for the next 5 minutes so that we can understand this particular, what is a supervised learning model, which is Navy-based classifier. So what we are doing is, we are assuming that the data follows normal distribution, right? We are assuming that the data, when you plot the data, it follows a normal distribution, right? In order to check whether this is following normal distribution or not, what we are doing is, we are what is say, collecting the data. So how do we collect the data? We, as this is not 1 minute. Labels and data are there here. So simply what we do is data dot, we'll check data dot. So we'll just connect to the RAM and disk. Right. We would like to save this. Is it possible to do? We'll see. So data dot, are there any methods? We'll see, are there any methods to save this data? Data dot to file, we have the method called data dot on data variable. We have the method called to file. To file, you specify the name of the file. Right? What is the name of the file? So gear attributes, right? Gear attributes, gear data dot CSV. We'll check whether this will give us a CSV file or not. We'll run this code. Yes, it has generated a CSV file for us. So gear underscore data dot CSV. So I am downloading this, and what I will do is I will quickly show you up what happened. I have you have the permission. You are unable to open this file. Restore this backup and gear data. So what is the problem? So 1 minute, I'll check WordPad if it is there. It is not showing us. It should show us the data, right? To file, it is writing CSV file. What is the problem? Enough disk space. File, I think we can see this later. Of course, data is now getting generated for 500 samples with 5 attributes. And what we are doing is this is also a binary class information, binary label. So we are specifying 2 labels here. And what we are doing is, once again, we are splitting the data into train and test. And 70% of the data goes to training and 30% of the data goes to testing. And what we are doing is we are calling Gaussian naive Bayes classifier. Right, Gaussian naive Bayes classifier. And once again, I place the cursor here to know what could be the hyperparameters. So Gaussian naive Bayes, 1 minute. So it has only 2 hyperparameters, priors and where smoothing, right? So here we don't specify any prior information for the class. So let us say if I specify priors also, what happens, we'll see. Priors is equal to what is the prior information that we have? What is the prior information that we have? Y underscore what is say we are using test label, right? Or train information, Y underscore train. Right, I'm passing priors to be Y underscore train. We'll check what happens, right? And we are using Gaussian naive Bayes classifier, and we are fitting the curve, right, with the train data of X and Y information, right? Training data set we are using to fit the curve, or let us say we for learning the naive Bayes classifier. And once the naive Bayes classifier is learned, LHS of the mathematical representation is learned, upon that we are using the predict method and we are passing the test example, and that text example is passed here like this, and which generated a message saying that the gear is predicted to be defective here. But we'll check now. I'm passing what priors to be y underscore train. We'll check what happens. So what is that? It is saying number of priors must match the number of classes. Okay, so fine. Number of priors must match the number of classes. I'm saying priors equal to 2. Fine. So simply I run this. But still, what is the priors parameter of naive Bayes must be an array like or none. Got 2 instead. So array means labels. If I pass labels, what happens? We'll see. Fine, labels. It should take, right? Labels must be labels. It should take labels because labels are nothing but the values. Check. We'll check. Labels instead. Okay. Fine. So we resort to the value of none here. None. So what is the prior information that we have? Cursor, if I place here, priors equal to none. So we resort to the value of none, priors equal to none. So automatically the interpreter will consider the prior values to be the number of class labels, which is nothing but 2, right? So simply run this. So it is 56% accurate, and it is saying the gear is predicted to be defective. Now what I do is quickly I will check what these attributes are saying, what the hyperparameters are saying. Hyperparameters. The prior probabilities of the classes, if specified, the priors are not adjusted according to the data. So where smoothing, default value is this one, portion of the largest variance of all the features that is added to the variance for calculation stability, right? So these are the parameters we need to use. So we are not concentrating on these parameters as such now. So the priors are not adjusted according to the data. As we are passing the data, it is better not to specify these priors. So that's why we specified the priors value to be none, and which is nothing but the default value, right? And variable smoothing, we are not at all working. We haven't seen how much variance is there in the data of all the features, right? If as we have don't know what is the variance of all the features from the data, it is better not to use this attribute var underscore smoothing, right? So if you know what is the variance in the from the data, then you can simply update this value, right? As we don't know, it is better not to use that attribute or use that hyperparameter and see what will happen, right? But this is what is the working of naive Bayes classifier. Everything is boiled to simply a what is a um, instance of a class, right? So Gaussian NB is an instance of a class named Gaussian NB, right? So you are creating the instance of the Gaussian naive Bayes classifier, and you are simply using that classifier for the sake of training and prediction, right? So any doubts here? As participants, if you have any doubts, you can now raise. as the participants are informed to raise the doubts if there are any. So this topic in itself is very heavy, right? So I tried my level best to cover all the important topics with respect to supervised learning, right? And these topics are pretty much important for better understanding of and working with the supervised learning classifiers. So as we have seen now, how modifying the values of hyperparameters will give us a new model altogether. So this is all about working playing with these variables like hyperparameters and parameters. Yes, hyperparameters and parameters, and checking the cross checking the what to say theoretical aspects and understand in a better fashion, right? So while prediction also, you can modify these values and check how the model is performing, right? How what kind of message it is throwing back finally. You can simply modify the test portion of the data and check it. Okay, so if there are no doubts, then I think I can stop this session. Sir, Srinivas sir,
Sir.
uh,
Sir.
I think the today's session is complete.
Okay, sir. Participants are having any doubts, you can ask. No, sir. Okay.
Okay,
Tomorrow morning, the session begins at
10:30.
10:30.
Okay.
Okay, sir, then.
Okay, sir. Thank you, participants, for your patient listening, and we will meet again tomorrow at 10:30 p.m.
10:30
Yes, or 10:30 a.m. Sorry,
AM.
AM.